Lose one disk in a RAID 0 array, lose everything, no parity, no mirror, no recovery. 2 terabytes of evidence, gone because someone optimized for speed instead of safety. This is why a CHFI does not skip the storage layer. You need to know what is under the file system, disk geometry, partition tables, RAID, slack space, hidden areas. Get this wrong and you image the wrong sectors, or miss the evidence sitting in plain sight. Start at the metal, HDD geometry, platter, circular magnetic disk. Most drives have several stacked, track, concentric circle on a platter surface, hundreds per surface. Sector, smallest physical unit, traditional 512 bytes, modern 4096, advanced format. Cylinder, every track at the same radius across all platters, a vertical stack. Head, read-write mechanism, 1 per platter surface. Cluster, logical group of sectors, smallest unit the file system allocates. Then addressing. Legacy was CHS, cylinder, head, sector. 8 GB ceiling, obsolete. Modern is LBA, logical block addressing. Sequential sector numbers starting at 0, used by every modern drive on the planet. Now the big one, SSDs break forensics. An HDD stores data on magnetic platters. Deleted sectors stay readable until overwritten. Recovery rate from unallocated space high. An SSD stores data on NAND flash cells. When the OS deletes a file, the trim command tells the controller these cells are free, and the controller immediately zeroes them. Your write blocker did its job. The trim operation happens inside the drive, independently. Wear leveling moves data to balance cell wear. The LBA you read does not match where data physically lives. Garbage collection runs in the background, destroying deleted data even without trim. Over-provisioning hides 7 to 28% of the drive from the OS. Exam takeaway. Deleted file recovery from SSDs is often impossible. Check trim status before you image. F-pseudo behavior query. Disable delete notify. 0 means trim is on. Disable it if legal hold allows. Partition tables, 2 formats, different worlds. MBR, master boot record, lives at LBA 0. 512 bytes total, boot code 446 bytes. Partition table, 64 bytes. Signature 0x55AA at the end. Maximum disk, 2 terabytes. Maximum partitions, 4 primary. Partition types identified by a 1 byte code. GPT, guide partition table. Lives at LBA 1. Protective MBR sits at 0 for backward compatibility. Maximum disk, 9.4 zettabytes. Maximum partitions, 128, each identified by a 128-bit GUID. And critically, GPT stores a backup header and partition table at the end of the disk, recovery capability built in. Required for UEFI boot. Required for drives over 2 terabytes. 2 boot sequences, no both. Legacy BIOS boot. Post runs first, power on self-test. Hardware initialization BIOS reads the MBR from LBA 0. MBR boot code loads the VBR, volume boot record of the active partition. VBR loads the OS bootloader. Boot MGR on Windows. Grub on Linux. Bootloader loads the kernel. Then UEFI boot. The modern sequence. UEFI firmware initializes hardware, reads the GPT partition table, locates the EFI system partition, typically FAT32. Loads the EFI bootloader from the ESP. Bootloader loads the kernel. Forensic note, bootkits infect MBR, VBR, or EFI. Bootloader. Secure boot validates signatures. RAID. Redundant array of independent disks. Multiple drives combined for performance or redundancy, or both. RAID 0, striping, no parity, no redundancy, best read and write performance, worst forensic recovery, lose any disk, lose everything. RAID 1, mirroring, 2 disks holding identical data, can image either mirror. RAID 5, striping, plus distributed parity, tolerates one disk failure. Forensically, reconstruct from remaining disks using parity math. RAID6, striping plus dual distributed parity, tolerates two disk failures. More complex reconstruction. RAID10, mirror plus stripe, best performance plus redundancy. Image both mirrors of each pair. Forensic rule, image every individual disk first, then attempt array reconstruction virtually. If reassembly fails, you still have the individual disks. Slack space, the difference between logical file size and physical space allocated, where old data hides. 4 types you need to know. RAM slack, between end of file and end of sector. In older systems contained RAM contents. File slack, also called drive slack, between end of file and end of cluster, filled with old disk data. Highest forensic value, may contain fragments of previously deleted files. Volume slack, space between end of partition and end of volume, may contain previous partition data. Partition slack, between adjacent partitions. Anti-forensic hiding location. Quick math, file size 5,000 bytes, cluster size 4,096. 2 clusters allocated equals 8,192 bytes. File slack equals 3,192 bytes. 3K of potentially recoverable old data for one file. Hidden areas, anti-forensics goldmine, HPA, host protected area, reserved at the end of the drive, not visible to the OS. Set with ATA setmax address commands. Vendors use it for recovery partitions. Attackers use it to hide entire file systems. Detection, HD PARM-N versus HD PARM-I. If the values differ, HPA exists. DCO, device configuration. Overlay, more powerful than HPA. Can permanently hide features and storage from the OS and from software. Detection, HD PARM-DCO-identify. Remapped sectors, bad sectors moved by firmware. The original sector data may remain, requires specialized tools, not accessible via normal reads. 3 of the most common places attackers hide evidence, and most amateur examiners never check them. Lock the layers, geometry, sector cluster, LBA, partitions, MBR for legacy, GPT for modern, boot, BIOS to MBR to VBR, or UEFI to GPT to ESP, RAID, image each disk first, reconstruct second. Slack space, file slack is the prize. Hidden areas, HPA and DCO, check them. Next up, Objective 3.2, file systems across Windows, Linux, and macOS. Once you understand the disk, you need to understand the language the operating system speaks to it.